Dear students, so now we will discuss another important term used in analytical mechanics, which forms the basis of certain principles like D'Alembert's principle. The term is virtual displacement. So let's see the definition of virtual displacement first, so that we will get some background of what we are going to discuss shortly. In principle, a virtual displacement is defined as an imagined infinitesimal and instantaneous displacement of the coordinate that is consistent with the constraints. So let's try to break up the definition. It's containing three conditions. One condition is that the displacement is imaginary. It's not a real displacement, it's only an imagined displacement. Second one is that this displacement is supposed to be infinitesimal, means its magnitude is very small, infinitesimally small. Third criteria for calling a displacement as a virtual displacement is that it should be instantaneous. Of course, this term is a bit abstract, but we will make meaning for this term as well. Now, the most important thing that you have to note that this type of displacement should be consistent with the constraints of the system. What is meaning consistent with the constraints? Means these displacements in no way can affect the already present constraint. It should not disturb the constraints. Means only those displacements are permitted which will not violate any of the constraint that exists in the system. So those displacements which are imaginary, which are infinitesimal and instantaneous, as well as those which do not violate any of the constraints of the given system, can be regarded as virtual displacement. Now let me give you one example so that will make it clear. See, you consider our common system. So you'll see that a simple pendulum is such an example of physical systems which will help us to learn many things. So here we are trying to understand the concept of virtual displacement with the help of a simple pendulum. So in the figure here, I represented a simple pendulum which is suspended from some pivot point O, and I have shown two positions. I have shown two different positions of the simple pendulum. See, let me say that at any instant t, let the position of the bob be shown by this particular orientation, means the black line and the black bob, right? Now what I'm going to do, I'm going to imagine, see, I'm not letting the bob to move, but instead I'm going to imagine. That is something very important. I'm going to imagine another position that can be attained by the bob at the same instant. Means at a particular time t, either the bob can be at the first position or the bob can be at another position. I don't say that these two are the two different positions of the bob. No, these two are the two possible positions of the bob at any instant t. So there is no any time difference between the two positions that have shown. Means I am imagining two possible configurations of the system which is consistent with the constraints. Why do I say it is consistent with the constraints? Because you know that without violating the constraint. What was the constraint of this simple pendulum? The constraint of the simple pendulum is that the length of the string should remain constant. We have already seen that. The length of the string should remain a constant. That is the constraint of the simple pendulum. So whatever displacement that we can imagine without affecting the length of the string, and which is infinitesimal, means which is very small in magnitude, and also which is what? Instantaneous, as I told you, because it is imaginary, is regarded as the virtual displacement. So let me show that. Okay, suppose, so here the displacement will be some angular displacement. You can just say this is angular displacement, and let me say that let this angle be some theta. The angle made by the string of the pendulum with the vertical, let that be theta. Now I'm imagining a very small angular displacement here, very small angular displacement, and this angular displacement I'm representing by some delta theta. See, I'm not writing d theta, instead I'm writing delta theta, and that is a mathematical symbol that is accepted for representing virtual quantities in analytical calculus or in analytical mechanics. And you know, corresponding to this delta theta, there will be of course a linear distance traveled, of course, which will be nothing but the arc of this so the length of this arc, of course, that will be equal to L into delta theta. So if you want, you can just L length angle equal to arc by radius, you can use it, and so this will be equal to L into delta theta. So if the condition is that this delta theta should be infinitesimally small, okay, then we call this displacement. So here this delta theta in my diagram is what represents what? The angular virtual displacement. Okay, so this one can be the virtual displacement. So now we'll make it more clear with arguments. Or it can be L into delta theta, which is nothing but what? The corresponding linear virtual displacement. So both of this can be regarded as per the need. Okay, now let's analyze why this condition consistent with the constraint. Okay, so our particle here is this bob, right? The bob of the pendulum is our particle having some mass em, you say, right? Now think of in what all ways this bob can move, in what all different ways this bob can move. Okay, so as we have seen that the bob can either move to this side. Okay, so the bob can move to this side, as we have just considered. Imagine the bob can move to this side, both following the arc of a circle. That is permitted, of course. Okay, because moving along either of this direction is not going to affect the constraint. It will retain the length of the string as L itself, because it is moving over the arc of a circle, right, with L as the radius. Now you think of, because it's our freedom to imagine, because all these say displacements we are imagining only. We don't really move the object. It's only just like what is known as this is what exactly this is just like a thought experiment. Remember, in the virtual displacement theory, the two positions that we are taking, between which there exists a displacement, imagined displacement, is just like the two positions in a thought experiment. It's not a real procedure or real experiment that we are doing. We don't actually move, but we imagine two equivalent positions which are consistent with the constraints of the system. So these are something like a thought experiment. That is what we can use. Now see that you consider you imagine the bob to be moving along this direction, or the bob to be moving along this direction. Can you just move the bob along these two directions? Of course you can move it, but certainly it will affect the length of the string. If the string is so by principle or in principle, the length of the string should remain constant, or it is an inextensible string. So if you try to move it along radial direction, then certainly you are trying to disturb the constraint, right? You are trying to disturb, or you are trying to violate the constraint. So such a type of displacement cannot be regarded, or those types of displacements are not considered to be what is known as what? A permitted virtual displacement. So those imaginary displacements that you can think of regarding a system which will not in any way violate the already present constraints in the system can be a virtual displacement. So the three conditions I have just summarized here. One thing, always remember, the virtual displacements are imaginary, so which I have highlighted. The virtual displacements are not real displacements because they are not caused by any applied forces. Okay, why they are not real displacements? Why the word virtual? That's what I'm trying to explain. Why the word virtual? Because this is most often a misunderstood concept. Okay, or what I can say is that often confused about why the word virtual displacement, what is the need for virtual displacement, etc. in our these topics. The word virtual is used because it is not a real displacement. It's just an imaginary displacement, as like what is done in a thought experiment. Okay, it happens instantaneously. I'll tell you why it's said to be happening instantaneously. Okay, virtual displacement because it's imaginary. And why it is not why it's imaginary? Because it is not caused by any applied forces. It's not caused by any applied forces. It's just the outcome of our imagination. That's why it's known as virtual. Okay, rather it is the difference between the equilibrium position of the system and an imagined position. Okay, I repeat, a virtual displacement is the difference between the equilibrium position of the system and an imagined position. By equilibrium position, okay, it can be like, see, don't confuse it with what, see, just like it can be like this also, okay, this is usually the position of stable equilibrium. So you imagine initially the bob is here, you can imagine the, see, the bob to be just displaced here. You are not displacing it with the evolution of time. Instead, what you are imagining, two equivalent positions which are consistent with the constraint. So I am repeating it time and again. You do not give a real infinitesimal displacement. So a real infinitesimal displacement will involve evolution of time. Okay, because at the same time the bob cannot be here and cannot be here. So it cannot have both the positions at the same time if it is a real displacement. So certainly maybe one is the position of the bob at a time t1, and 2 will be the position of the time position of the bob at a time t2. Okay, and the time interval between t1 and t2, say t2 minus t1, I can call it as dt, and this dt is not equal to 0. Maybe you can say that dt is tending to 0. Okay, dt is never equal to 0 in a real displacement. But remember, in the concept that we are discussing currently, which we call as virtual displacement, the dt is regarded to be 0. dt is taken to be 0. Why do we take dt equal to 0? Because it is not a real displacement. These are two permitted or equivalent positions that a system can take up at the same instant. It can either be there or it can be here. Okay, so it's not that you are moving from one place to other. So we imagine two permitted positions at the same instant. So it's just like, okay, you have taken two snapshots of the system in two different instants, but you just look at the two snapshots together and you say that both of these are permitted. Okay, both of these are just like the permitted positions, configuration of the system consistent with the constraints. So there is no any time difference involved in a virtual displacement. That is due to that reason we call that a virtual displacement is instantaneous. Okay, so we usually write that, okay, second one, I can say second condition for calling a displacement as virtual displacement is that it should be instantaneous. I'm not keeping the order, I know. Okay, instantaneous in the sense that there is no time evolution. There is no time evolution that's considered. Or I can say the virtual displacements are usually written as delta R. Okay, and remember, real displacements are represented by dr usually. No, we used to write R, if the R is the position vector, then dr represents the displacement vector, right? Which are real displacements, which happens with the passage of time, with a time interval of dt between the two positions. Okay, so usually we say that this delta R this delta r, or the virtual displacement delta r, is regarded as the displacement dr which happens at, or which happens with the condition that dt equal to 0. It's okay, something interesting. So delta r can be regarded as the displacement dr which occurs during dt equal to 0. Means dt equal to 0 means we don't consider any time evolution. Okay, so that's mean. So that is why it is known as instantaneous, because both the positions are permitted, because they are imagining. So we imagine that. We cannot say that I imagined this one first and I imagined the other one late. Okay, we can imagine both the states together. That's why it is known as what? Instantaneous. Okay, or it's also known as what? Virtual. It's not real, because it's not caused by any of the applied forces. Now, okay, and why do we do all this? Why do we take all this pain? Only because what? Such a thought experiment gives you a mathematical technique to solve mechanical problems without bothering about tensions, without bothering about constraints. You need not bother about the presence of constraints in a mechanical system once you are ready to take this pain of imagining what is known as a virtual displacement. Okay, so I will just demonstrate one or two examples how the concept of virtual displacement will simplify the solution of a mechanical problem. How you can get rid of the tensions due to tensions, or due to the presence of constraints. I take tension here as an example, a very visible example, a very familiar example of a constraint force. Okay, now see, I say that it is consistent with the constraints. Here, what is the constraint force here? Constraint force is the tension in the string. Okay, so without affecting the tension in the string, you can just see, without disturbing the tension. Okay, you will be able to, if you are able to make a displacement, then we will call that displacement as what is known as the virtual displacement. Okay, this is what I want to tell you. So it is usually regarded as the difference between one position, which is usually regarded as the equilibrium position, means permitted position, that is what I mean, of the system, and an imagined equivalent position which is consistent with the constraints of system. Okay, and this position will be imagined as slightly away from the equilibrium position, slightly away from the equilibrium position. That is why, okay, the magnitude of this displacement is taken to be what? Very, very small. Okay, that is a usual condition that we take while defining infinitesimal quantities. Okay, so it is a purely imaginary one. It's a sort of thought experiment. It's the outcome of a thought experiment. That's what I want to mention. Now we make a very important postulate. We make a very important postulate, and this postulate has been supported by the specific examples. Or this postulate that we are going to make, or this assumption that we are going to make, is based on our experience with the known force of constraint. So what is that postulate? See, the work done by the force of constraint in such a virtual displacement is 0. The work done by the force of constraint during a virtual displacement is 0. Okay. So a logical conclusion, the logical conclusion or the logical support for this assumption can be like this, because as I mentioned, that a virtual displacement is not caused by any real forces. A virtual displacement is not involving the actual motion of the system. As I told you, the system is not moving during a time interval dt. Okay, so the system is imagined to have two equivalent permitted positions, and the difference between those two positions is what is regarded as what? The virtual displacement. So since the virtual displacement is not actually the outcome of a real applied force, we can say that, okay, the work done by the force of constraint in such virtual displacements is what? 0. And that is a logical argument in favor of this assumption. And this has been proved correct, or this has been established in known examples. For example, you consider the case here itself. See, in the case of the pendulum here, which is a force of constraint? Of course, that is tension. And you know the direction of tension okay, it will be always perpendicular. It will be always perpendicular to what you say, okay, this sorry, the direction of tension will be along the string away from the mass. That's of course, okay, because tension is always a pulling force. It will never push the bob, right? So tension is along the okay, string towards the pivot point, as I have shown in the arrow here. So this is the direction of tension, okay. And see, our permitted displacement, say, let me say that this is the linear displacement here. So let me use and the color, okay, yeah. So here we have represented, this is the, okay, no, I think you are able to see this one. This is the permitted linear virtual displacement, which I have represented by L into delta theta, okay. So linear virtual displacement, and delta theta is the corresponding angular virtual displacement, okay. Now you can see that what about the angle between the tension force, which is a constraint force, and the virtual displacement here? Of course you can see that is 90 degree, right? Okay, so the radius and the tangent are always perpendicular. That's the property of a circle. So you know they are 90 degree. And you know, how do you calculate the work done by a force? You know, work done by a force is usually calculated as the dot product between the force and the displacement, okay. So work done by the force of constraint, work done W here will be equal to the force is tension, okay, the force is tension, okay, T dot this, what do you call, AB or something you can call, or you can write L delta theta. Let me call it as AB vector. That's always better. AB vector, where I am see that this is A and this is B, okay. So AB vector, this one is AB vector. So you can see that since they are perpendicular, okay, so it will be equal to 0, right? So the work done by the force of constraint is equal to 0, right, in what is known as a virtual displacement. Other force of constraints, for example, when an object is moving over a plane surface, okay, if an object is moving over a plane surface, you say that on a table, okay, on a table, an object is made to move on the surface of the table, then of course the force of constraint is nothing but what you can call the normal reaction, okay. The normal reaction on the body of mass em is nothing but the force of constraint, okay. So the weight is exerted downward, so there is a normal reaction on the object, right? So the force on the object is actually the normal reaction, which acts perpendicular. And in what way the bob, the mass will be moving over the surface? Of course, it will be moving along the surface of the, okay, plane, right? So what about the force of constraint, the angle between the force of constraint and the direction of virtual displacement, okay, which is consistent with this constraint, okay? That will be again what, 90 degree, because the normal reaction is always perpendicular to the surface there, right? So here also the work done will be equal to 0. So we are bound to believe that the work done by the force of constraint in any virtual displacement is what, 0, okay. That's the basic assumption. So we I think we can just go to the conclusion. Yeah, I have already mentioned that the virtual displacement is the difference between the equilibrium position of the system. Usually we can regard, okay. So if you consider one of the equilibrium positions, say like I can take this one as like these two. So the virtual displacement can be regarded as the difference between the equilibrium position of the system and an imagined position, which is consistent with the constraints of the system and slightly away from the equilibrium. So that can be a best definition for virtual displacement. You need not take it always to the extreme positions, okay. You can take it to the real equilibrium position, which is in the case of simple pendulum, which is what at the mean position. So that's the definition of virtual displacement, right? Now we'll see its advantage of having such a concept in solving the problem. Before going to that, let me just explain what is known as virtual work, because our motivation behind defining a quantity known as virtual displacement is in order to define a quantity known as what, virtual work, okay. Once the concept of virtual displacement is clear to you, if you agree to, okay, if you agree to just accept this particular concept, then it will be quite easy to deal with the concept of virtual work, which is just an outcome, okay. So let's see now what is virtual work. Virtual work is represented by delta W. See that this terminology or this symbols that we are using, D for real, okay, like dW means an real infinitesimal work, okay, so real work, and delta W for virtual work, and that is the language that we will be following in analytical mechanics. Okay, so let's see what is the definition of the virtual work. Work done by any force, on a particle due to its virtual displacement. Okay, or we can say that work done by any force on a particle which produces what? A virtual display. Okay, a virtual. So I'm not satisfied with the word. Okay, what is that? Which produces, because we have already accepted that the virtual displacement is not actually caused by what? Any applied forces. Okay, so better we will satisfy ourselves with the definition that, because anyway it won't suffix the definition of a real work. That is why we are feeling a difficulty. So work done. Okay, usually you know that we can calculate the work done, or we can relate the work done with the some force and a displacement. Some force and a displacement which the force produces. Usually that is the way in which we have been doing. Okay, so W or dW is equal to F dot dr. That is what we have been doing in the case of real work done. And in the same line, along the same conceptual line, we are trying to define what is known as virtual work. How do you define it? The thing is that the force may be real. The force, okay, may be real. The force acting on the particle is real, but we are calculating the work done corresponding to a virtual displacement, which is imaginary. So the virtual displacement being imaginary, the corresponding work done that we are calculating as the product of the applied force and the virtual displacement is also taken to be what? A virtual work. Okay, so the work done by any force on a particle due to its virtual displacement or corresponding to the virtual displacement. So instead of the word due to, it's better conceptually corresponding to. Okay, because it's in the lines of the definition of a real work, corresponding to its virtual displacement may be regarded as, or may be called as what? Virtual work. So how do you define it? The virtual work done, suppose that you have a system of n particles. So for a system of n particles, so let me just go to some mathematical symbols. For a system of n particles, okay, that is let me say I or j equal to running from 1 to n, right? For a system of n particles, let me consider the virtual work done on the ith particle. Okay, the virtual work done on ith particle. We are considering a system of n particles, and I'm considering the virtual work. The virtual work done on the ith particle by some force, by some applied force, okay, or some total force, ith particle. Let me denote it by the symbol delta. You know, virtual work we are representing by delta W, and to denote that it's on the ith particle, we calculate individual work done. Okay, I'm writing delta Wi. So what it will be equal to? It will be equal to the total force acting on the particle, means on the ith particle. So I'm writing Fi. Fi is the total force acting on the particle. Fi dot the virtual displacement for the particle, delta Ri. Fi dot delta Ri, right? So this will be, okay, let me call this one as equation number 1. That's the definition for the virtual work done on the ith particle. I think, okay, you always compare this equation number 1 with this standard equation of work, infinitesimal work done in mechanics. This is real work, real infinitesimal work, and you just compare the symbol differences. Okay, instead of dW, I have used delta W. Instead of dr, I have used delta R. So that makes it virtual, because it's conceptual. It's an imaginary technique, just a technique. We don't do it. Okay, we imagine, okay, such a thing is done, and we have got its benefits without much pain. We'll see that. Okay, right. So let me come back. So what is delta Ri? Delta Ri is the virtual displacement of the ith particle. Okay, and delta W is the corresponding virtual work done. Now, you know, if you want, what we can do, Fi here is the total force acting on the ith particle. So we can just break up this total force on the particle. Fi can be broken up into two components. Fi is the total force, or instead of the word total, since it is a vector, it's better that I use the word resultant force. Okay, because forces are vectors, so total here means the vector sum, right? So Fi is the resultant force of two other, or resultant of two other forces. Which are forces? There can be some external force, whenever there is a system, okay, there can be an external force which is acting on the system. I'm writing as Fie, or I can write Fia. A means applied. External forces are otherwise known as applied forces. Okay, and these systems are moving under some constraint forces, right? So let me consider the presence of the constraint forces also. Okay, so let me say that Fi, I'm writing vector Fi, small Fi, let that be the constraint force that is acting on the ith particle. So what will be the total force acting on the ith particle? It will be the resultant of the external force or the applied force on the ith particle, and what? The constraint force that is also acting on the ith particle. It can be due to various reasons. The constraint can be due to various reasons depending on the system. Okay, so this is what I'm doing. So let me call that this is some equation number 2, right? Now, see, always remember where these terms are having its own meaning, what I explained, where Fi is the external or applied force, and Fi is the force of constraint. If there are several force of constraints, okay, then Fi is nothing but the vector sum of all those force of constraint, complete force. Okay, therefore, how can I rewrite my virtual work on the ith particle? Delta Wi, which is a scalar, that is equal to, I can just break up that Fi as what? Fi, okay, external or applied plus what? Fi, I means on the ith particle. I'm calculating individually. Fi, which is what? Due to the constraints, dot delta Ri, where delta Ri is the virtual displacement of the ith particle. So this is the detailed equation for the virtual work on the ith particle. Now we are in a position to define what is known as the principle of virtual work. The principle of virtual work. Okay, so I think I will define I will just explain the principle of virtual work using this equation 3, and then we will just explain, or we will just discuss some physical examples of this principle in the next video. Okay, just a moment. So let's go to the principle of virtual work, and that was our A. See, here I have just given the principle of virtual work. Let's first read this principle. This can be taken as one of the statements. For a system to be in static equilibrium, see the word static equilibrium, the virtual work done by all the external or applied forces should be 0. Okay, and that we know. This is nothing new. We feel for a system to be in static equilibrium, the virtual work done by all the external or applied forces should be 0, provided there is a condition, and this is the soul of the principle of virtual work. Provided the virtual work done by all the constraint forces is 0. So remember, the principle of virtual work is based on our fundamental assumption that the virtual work done by all the constraint forces is 0. If that is the case, the system can achieve a state of equilibrium, static equilibrium, if the virtual work done by all other external forces is also 0. Try to digest the statement. It's a conditional principle. Okay, what is that? If the virtual work done by all the constraint forces is 0, then the virtual work done by all the external or applied forces should be 0 for a system to be in static equilibrium. Or I can say, what is the relevance or what is the significance of principle of virtual work? The significance is that this principle gives you the condition for a mechanical system to be in static equilibrium. So the principle of virtual work deals with the condition for a system to attain static equilibrium, and finding the possible equilibrium configuration of a system is very, very important in many physical systems, many engineering applications. There are a number of applications for this principle, especially in engineering, especially in civil engineering, when you design that truss work. Nowadays we know that we are most of the buildings are having truss work on it. We make connections by with rods and all, and in different designs are done, and or we can say that we have a large number of bridges which are made up of steel, hanging bridges. All these constructions, that we have to make sure in the very design by the engineering side itself that they are stable. Okay, I'm not talking about concrete bridges. Okay, I'm talking about those bridges which are made up of steel or such things. Okay, and there are a lot of constructions which are prefabricated constructions. So the design should be in such a way that the different parts should be connected in such a way that the system is finally in static equilibrium. And how do we design those things, or how do engineers design those things? Actually, the principle of virtual work is of great help to them. So this principle is mostly used by engineers in the design of stable systems, stable building systems. Okay, so we'll see some examples if time permits. Of course, the references are engineering physics textbooks or civil engineering textbooks will be the best reference for this particular topic, because we as normal physics people, we do not deal much about what the principle of virtual work, its application and all, because our aim is to just reach another fundamental principle in analytical mechanics, which is known as the D'Alembert's principle, which forms the basis for deriving the Lagrange's equation of motion. Okay, that is the reason. So anyway, let me come back. So this is the principle of virtual work. So let me just explain the principle of virtual work. It's quite simple. Let's that for a system to be in static equilibrium, the net force on the system should vanish. Is not right? That is our pure mechanical concept. Is not for a system to be in static equilibrium, static equilibrium, net force should be equal to what? 0, right? The resultant force should be equal to 0. Then you can say that it can be in static equilibrium, right? It can be in static equilibrium, that net force on the system is vanishing. Okay, now the virtual work done on such system due to any arbitrary virtual displacement, what will be the value? Okay, we have first of all made sure that the system is already in static equilibrium, since the net force acting on the system is what? 0. Okay, so to this system which is already in static equilibrium, let's assume some arbitrary virtual displacement is given. Let's assume a virtual displacement, any arbitrary virtual displacement is given to a system which is already in what? Static equilibrium, due to the vanishing of the net force on it. Okay, so let's say what will be the virtual work done on such system. The virtual work done on a system in static equilibrium. What will be the mathematical expression for that? Okay, so on the system in static equilibrium, that is what we have to do. Okay, to do this one, what I'm doing, I'm first calculating for the ith particle. Okay, for the ith particle I can write what will be the definition of virtual work done for the ith particle. for the ith particle. So it's an n particle system. I'm calculating the work done on the ith particle, and then I will sum it up. Okay, so what is that? Delta Wi, that will be equal to, you know how to write it. We have written it some equation number 3 earlier. Fi external plus what? The Fi, which is the force of constraint, dot what? Delta Ri. And what will be its value as per our idea? We assume that this net force is equal to what? 0, right? So I can say this one will be equal to what? 0, right? Okay, for the see, when you take the summation, it will be equal to 0. So here say that I can run from 1 to n. Now total virtual work done on the system. How do you get it? So in order to do the total virtual work, let me write that will be equal to total virtual work. Total virtual work. Okay, we said delta W. Okay, so delta W, that's equal to sum over, is not, delta W will get by adding up all the individual work done on individual particles. So sum over I equal to 1 to n, I equal to 1 to n of this delta Wi. That is what? Fi external plus what? Fi dot delta, of course here delta Ri should be there, delta Ri. Okay, and since the system is in equilibrium, you can see that this delta W should be equal to 0, right? The virtual work done on the system will be equal to 0 because the system is already in what? Static equilibrium, right? So this is equal to 0. Now let me break up this one into two terms. How do I do? So I can write as what? Sum over I equal to 1 to n Fi external dot delta Ri plus again sum over I equal to 1 to n Fi means force of constraint dot what? Delta Ri, that should be equal to 0, right? But we have a fundamental assumption in the principle. What is the fundamental assumption? The virtual work done by all the constraint forces vanishes. Okay, so due to that initial condition, this term is equal to 0. The second term is equal to what? 0, because the work done by the force of constraint is 0, right? Which we have argued, which is from our experience with the specific examples. We haven't seen or we are not able to find violations of this thing in ordinary holonomic constraint cases. Okay, conservative systems, holonomic cases, these types of violations of this particular examples or this particular assumption is not found. So we just agree upon that particular thing. The force, the work done by the force of constraint, okay, the virtual work done by the force of constraint is equal to 0. Remember, it's a virtual work. Virtual work done by the force of constraint is equal to 0, right? Now, if that is equal to 0, what does it mean? It means that, right? It means that, see, this Wi summation over I equal to 1 to n Fi, right, external dot delta Ri should be individually equal to what? 0. And what is this particular thing? You know, this is nothing but the virtual work done by the external forces. The virtual work done by the external or applied forces is 0. We have proved that the virtual work done by the external forces will be 0 if the virtual work done by the force of constraint is 0. And if these conditions are satisfied, our system will be in a state of what? Static equilibrium. So we have included that condition in the very first line itself. Okay, the very first assumption that we have begun with was the condition for static equilibrium, and due to that assumption only we were able to prove that this is equal to what? 0. And that if that equal to 0, we have seen counter argued that for that the delta W due to the external work, so the external force should be equal to 0. And this is the condition for static equilibrium of a system. Okay, and we'll see how the simple principle or simple concept of virtual work can be used to solve mechanical problems without bothering about the force of constraints like tension or normal reaction. We'll do that in the next video. Thank you.